How's it going, Professor?
Hey, how are you?
I'm good. Hanging out.
Yep.
I was gonna say, I don't think that you have the automatic mute setting set.
What is that setting?
Uh, I'm not sure. I think I've heard you mention it before in one of the previous classes, so I don't know. Thought I'd give you a heads up.
Automatic meet setting. Yeah, I reset it, the Zoom links every week because I can get it to repeat every 2 days or every 3 days, but I can't get it to do some particular schedule. And so I can repeat Monday, Wednesday, Friday, but then it will want to do Sunday instead of Monday. So I send a new link every week. And I think it's set up to repeat for this week, but yeah, I have to start a new one every week.
Gotcha.
Let's see. I'm sure there's a way around it. I just haven't figured it out. Let's get the dot cam going. And plugged in. This has been working better as long as I start Zoom first, I think. Okay. You're all welcome to give the warm-up problem a try. You're here early.
I've already submitted a response, but it's not showing up on the board.
Oh, okay. Let me reset the question then, see if that helps. Try now. I set this up with the waiting room by mistake. So I dumped you in the, if you ended up in the waiting room, hopefully I've moved you over and I've removed that option. No? Okay.
Yeah, that's for 30 minutes.
Unboxing.
Yeah, so a lot of you are being dumped in the waiting room. I'm admitting you as you end up there. What are the criteria for whether you get put in the class or put in the waiting room?
If you
I think
use
it might be a presetting.
Say it again.
I think it might be a setting like when you start the meeting.
Yeah, I accidentally set waiting room, but not everyone ends up in the waiting room.
if you open the link that you sent in the email, it should take you directly into the class. And if you just type in the meeting code, I'm pretty sure that's what drops you in the waiting room.
Okay.
I opened the link and I got put in the waiting room, I believe. So
I think it lets a certain number of people into the class, and then it makes everybody else enter the waiting room.
Okay. Well, I'm admitting everyone as they show up. I've changed it and resaved the settings, but I think it's too late for this session. Okay, we have about a minute till class starts. I'll keep admitting people that I accidentally pushed into the waiting room. And, but while I do that, are there any outstanding questions from last time? I'll have to just keep checking that periodically. So let's see, it is Monday, so another week begins, and we have a lot to cover today. The first thing on the to-do list is the warm-up question, and I see many of you have been answering it, so let me go over it really quick, and I'll give you a few more seconds to submit some answers. So this ties to what we talked about last time with Young's double slit experiment. Imagine a single photon is emitted by an atom, and it encounters Young's double slit experiment, so a wall with two slits, and then beyond that, a detector. So two questions. The first question is, which of the following is true? The photon travels as a particle, passing through one slit or the other. Or two, the photon travels as a wave, passing through both slits simultaneously. That's the first question. And then the second question is about detection. The photon is detected on the screen as a particle at a single location. Or two, the photon is detected on the screen as a wave with different intensities at different locations. So answer the first one, answer the second one, combine them, and push it up to the response screen. I'll keep admitting students while you're thinking. It says we have about 150 here, so let's see if maybe we can break 90 responses today. $88, $89, $90, $92, great. Okay, so let's see how you did. And we can have everything from 1-1 to 2-2. Eliminates a couple responses there. Show the histogram. Most of you say 2-1, and that's the correct answer. As we established last time, light travels as a wave. If you do this experiment over and over again, you see the interference pattern right there. This was done one photon at a time. That once we built them all up, we can see that it is indeed the interference pattern. So the light traveled through both slits as a wave, even if it was just one particle at a time, one particle emitted, one particle detected, but it traveled through the slits as a wave. Yet when it made it to the detector, it's detected at a single location. Light travels as a wave unless we try to look, and then it's magically a particle. And this is one of the biggest mysteries in physics, and it's just the way the universe appears to work. I don't think we have a great understanding of it yet, but the mathematics works, the physical models that we have work extremely well, and so we can use them as tools, even though it leaves you with kind of a sinking feeling inside that something is amiss. Okay, good. Next on my to-do list was explaining the polarization experiment from last time. So I'll just repeat it really quick. So we got the screen here, and I'll put up, a big blank screen. I'll get you all out of the way. And this one was just for fun. I mean, we were talking about polarization. And this is, again, one of our tests that light is a wave. We have a polarizer. And then we have another polarizer, which we put perpendicular, so nothing makes it through. And then we put another one in between them at a 45-degree angle. and magically the light does make it through again. And so I think that amazed and astounded some of you. It's actually something I only realized a number of years ago. I didn't always know about that trick. So let's put it back on down here. And does anyone want to venture a guess as to what's going on?
The 45-degree angle is like twisting the waves, kind of.
The twisting, yeah. There's another way to describe it that may be a little more accurate.
I was going to say, like, the change is gradual enough for the light wave to still fit through.
Yeah, you're getting closer. Anyone want to try one more time?
The light's bending around.
It's, yeah, so twisting, bending. I see where you're going. You're trying to get those waves as they go through to kind of change their orientation. What it is
Is the light, okay, I got my words mixed up, but I'm gonna just spitball them. Is it diffracting or reflecting or?
Refracting?
Yeah.
It's not those. It's actually components. So all of you tried different variations of trying to get the wave to change its orientation, either through diffraction, refraction, but it's actually just components. So let me draw it here. So most light that comes from space is unpolarized, which means, you know, you have a bunch of light coming through and all different polarizations are represented. And then you put down one polarizer in front, suppose it's oriented up, down, and only the up, down components make it through. It's not just this one that makes it through, but none of this one makes it through, but part of this makes it through, part of this makes it through. It's the part that is oriented the same with the polarizer. But anyway, I'll describe that in more detail in a second. You put one polarizer up and then all the light that makes it through is oriented up, down. If I put another polarizer perpendicular, as we know, nothing makes it through. If I orient the polarizer at a 45-degree angle, what we could do is take this light wave and break it down into its two components. You have some component that's oscillating with the polarizer and some component that's perpendicular. The perpendicular component doesn't make it through, but the component that's aligned with the polarizer makes it through. So then you have a smaller amount, but some amount of light coming through, and then it goes through the one that was perpendicular, and again you can break it into components. You have one component that's oriented with the polarizer, one that's perpendicular, so this component here makes it through. It's darker, less light makes it through, but through the components it makes it through. So that's the answer to that, if it was keeping you up at night. All right, let's see. Got one person in the waiting room. Admit them. And yeah, let's just continue where we were last time. I got a little bit farther with the other class. And so if you want to see this next bit in more detail, you can watch the tail end of the video that I posted last time. But I'll summarize it briefly because it is kind of important stuff. So we've established that light travels as a wave, both through diffraction and interference and also polarization. Detected as a particle, but it definitely travels as a wave. And so waves have properties, as we talked about. They have wavelengths, they have frequencies, they have energy. And so light waves should also be divisible into categories based on these properties. So you have a spectrum of different types of light, and we call it the electromagnetic spectrum, or EM spectrum for short. Let's see. Move this over here. Yeah, the EM spectrum for short. And here's just a depiction of it. We could take the light and break it into different bands. We're most familiar with the visible band, which runs from red to violet and all the different colors of the rainbow in there. And none of these bands are to scale. The visible band is actually a very small sliver of the entire electromagnetic spectrum. In other words, the visible band is what our eyes are sensitive to, and our eyes miss most of what's going on. We just got this little small window into the range of different types of light. Beyond visible, you have or I'm sorry, beyond violet, you have ultraviolet. And beyond that, you have X-rays and then gamma rays. And on the other side, beyond red, you have infrared and radio. And it's all light. It may sound strange, but when I talk about radio waves, I'll often describe radio light. If I mean light that is visible to the naked eye, to the human eye, we call that visible light. But you can have gamma ray light, infrared light, X-ray light. It's all different types of light. The only thing that's really distinguishing it is its frequency or the wavelength. Those two are interchangeable, or the energy. But
A quick question.
yeah, go ahead.
Shouldn't microwaves be on here somewhere, or do they not count?
Yeah, microwave kind of sits right here between infrared and radio. Sometimes they include it, sometimes they don't. You can think of microwaves as really short radio waves or really long infrared radiation.
Oh, okay, thank you.
These divisions are arbitrary, and astronomers will break them up even further. We'll talk about soft X-rays and hard X-rays and soft gamma rays, and a hard X-ray is the same thing as a soft gamma ray. So the divisions are arbitrary. All that's really changing is the frequency. Light's a wave, waves have frequency. Now, you can also, remember these two equations that we wrote down for waves. The energy of a wave is proportional to its frequency. And with light, that constant of proportionality is something we call Planck's constant, which is denoted with a little h. You'll never need it in this course. I would always give it to you in a ratio form. Like if I double the frequency of the light wave, I'm doubling the energy. And if you look at these different types of light, it makes sense. Here are the high frequency waves, and these are the more energetic particles. Ultraviolet can give you a sunburn. X-ray can penetrate your skin but not your bones, and hence doctors use it to image fragments or fractures. And gamma rays, the most energetic, they can mess up your DNA and cause cancer. Now the other equation that we had put up when talking about waves in general, I'm sorry, this curly V, that's frequency. It's the Greek letter nu. Now the other equation we gave was wavelength times frequency is the wave speed, and this lambda corresponds to wavelength. There we go, wavelength. And with light waves, they're kind of special compared to all other waves. All light waves travel at the same speed, the speed of light. It's a constant. And so these two are directly relatable. If you know the frequency, you can calculate the wavelength, or if you know the wavelength, you can calculate the frequency. And that's why on this plot here, you see two scales, frequency increasing to the right, wavelength increasing to the left, but they're interchangeable because all light travels at the same speed, speed of light. Okay, that was a little quick. If you want to see it in more detail, you can check out the tail end of the video last time, but I think we got all the basics there. So the next important question, now I'll go to a fresh page for this, is, I'll put the dog cam back up, waves in what? All waves require a medium. This is the first thing that we learned. Particle is its own medium. It can just travel by itself, but waves have to travel through something. So if light's a wave, what is it traveling through? Anyone want to venture a guess? There's a right answer that's subtle and a wrong answer that's standard. In fact, I think our textbook at one point even uses the wrong answer. And so I'm actually looking for the wrong answer first. So
is it a vacuum?
Vacuum, yeah, that's the wrong answer. So, and that's fine. I was asking for that first. So that's what most people think. Light travels in a vacuum, so vacuum would be the medium. But the definition of vacuum is the absence of a medium. A vacuum is nothing. And so if light's a wave, it has to be traveling through something, but it can't be a vacuum. That's the absence of a medium. So you only get it if you've done some advanced reading in the textbook. Anyone want to venture a guess?
Dark matter. I don't know.
No, not dark.
Electromagnetic field.
Electromagnetic.
itself.
Yep, that's it. And so there's kind of a hint there when I talked about the electromagnetic spectrum. Why do we call the spectrum of light the electromagnetic spectrum? Well, it's because the medium is the electromagnetic field. Now I'll take a little bit of explanation. It's subtle, it's not at all obvious. So electricity and magnetism, or electromagnetic force, it's a force of nature, electromagnetic. And it's one you've probably heard of, but it's not the one you're most familiar with. The force of nature you're most familiar with is going to be gravity. So let's actually just make a list of the forces of nature. The first is gravity. And that is, as we all know, it's an attractive force between masses. Many of you have probably heard of the electromagnetic force, and that can be attractive or repulsive. And it's between charges. Now I'll put that in quotes. Charges is just what we call the property. So here we have positive charges, negative charges. We know like charges repel, opposites attract. That's where that phrase comes from, opposites attract. It's another phrase that has its origin in physics, but has been used much more broadly. And so we call them charges, but really it's just some property of these particles that are opposite in nature. We could have called it up and down, black and white. Instead, we call it positive and negative charges. Okay, so that's the electromagnetic force, and we'll cycle back to that in a second, but just to complete the list, put the dot cam back up here. We have two more forces of nature. Does anyone know what they are?
Strong force and weak force.
Yep, the strong and the weak nuclear forces. And the strong force is what holds our nuclei together. Think about the nuclei, a bunch of protons and neutrons. Neutrons have no charge. Protons are all positively charged. They want to fly apart because of the electromagnetic force. Something even stronger is holding them together. That's the strong nuclear force. And then the weak force is really kind of strange. It's responsible for radioactive decay, for changing one particle into another. Anyway, these are forces that we cycle back to in Astro 102, and we've already talked about gravity a lot. So let's think about the electromagnetic force a little bit more, and we can break this down into two parts, the electric field and the magnetic field. For the longest time, we thought these were separate forces. It wasn't until, 200 years ago, we realized they're just two sides of the same coin. Let's take the electric component first, because that's the part that's most like the gravitational force. So here we have two charges, a positive charge and a negative charge. And in this figure, we've depicted the electric field using these lines. And the lines are a good kind of reminder that the field is there. Where the lines are denser, that means the field is stronger. So close to the charge, there's a large density of lines here. That just means the field is stronger, so the force will be stronger. And the farther away you go, just imagine extending these lines, they get farther and farther apart. So lower density, and so the field is weaker, and hence any force is weaker. So suppose this charge is stationary, maybe it's locked in place, it can't move, and we have some distant electron over here. Maybe this is a proton, this is an electron. The electron's going to feel this force and start moving towards it, just like masses would in the gravitational counterpart, the gravitational analogy. And as it gets closer, it's entering a region of more and more of these lines, a higher density of these lines, and so that means the force is stronger, and it will speed up and go faster and faster and faster as it approaches that charge. Let's see what is next. So next, right, so that's how the electric force works. Now, how can we have waves in the electric field? So for that, I'm just going to use the dock cam and kind of visualize it here. Light and just darken the room because I'm going to do a demo with lights. But yeah, so imagine this is our, just like in that figure, imagine this is the positive charge, and here I have a metal rod. And the nice thing about metal is it's conductive, so you can have charges flow through it, electrons in particular. And if I had a strong enough electric field, I could actually pull the electrons off of the metal rod, but usually that takes a lot. But as long as you're not applying that strong of an electric field, you are free to move within the metal. This is how wires work, electricity. We get the electrons to flow pretty easily through metal. So the electrons have a negative charge. This is a positive charge. And, if I hold a positive charge up here, the free electrons in this rod, where are they going to move? Yeah, they're going to move up to the top. And if I move the positive charge down, they will then follow in suit. Not instantaneously, it takes a certain amount of time for the force to propagate. Just like the gravitational force, it takes a certain amount of time. So if I oscillate the positive charge up and down, the electrons in the rod will also move up and down, but with a time delay. And just think about those field lines. Now, the field line is up here, and so it will follow, and then the field line is down here. So as I move it up and down, the field line is moving up and down, creating a wave in the field line. So I have a figure here that illustrates that from the textbook. It's ready. So here we're shaking a charge. Got some more people in the waiting room, I'll admit them. We're shaking a charge, and that's causing a ripple, a wave in the electromagnetic field. Here we're just showing the electric component, and then the distant charge feels that and responds accordingly. So this is the medium. The medium is the electric field. Here's the wave, and that wave is light. Now, it may seem really strange, but you make use of this every day. This is how your cell phones work. This is how the radio in your car works. You have a tower that's transmitting, and all they're doing is shaking charge. And so they're sending out light. It's not visible light. It's down in the radio part of the spectrum. And in your cell phone, you have a little metal bar, just like the one I showed in the prop over there. And it used to be that we'd pull them out of our cell phones to get better reception. Now they're just built into the cell phone. And so as they shake the charge, that sends a wave through the electric field that's emanating from that charge, and it causes electrons in the metal bar in your cell phone to oscillate in response. And you can encode information, as we talked about. You can encode information in a wave. You can modulate the amplitude, so you shake these charges with a large amplitude, then a small amplitude, then a large and a small, and you can encode information in the sequence, and your cell phone knows how to decode that information. So you can take voice, you digitize it, encode it, send it through amplitude modulation is one way, and then your phone undoes it. And of course, the other way is frequency modulation. We can have rapid oscillations and then slow, and then rapid and slow. So you can encode information that way. And it works in reverse as well. You're also a little transmitter, and the towers can pick it up, decode it, and send it on. Okay. Questions about the electric field before we get into the magnetic? All right. So I said these two always go together, and that's true. We realize they're a unified force. They're just whenever you change one, you generate the other. Or if you change the other, you generate the one. You'll never have one just by itself. An example is, let me put the dock cam up first. We'll come to the Earth example in a second. But imagine you just have a battery here with a positive and a negative, and then you run a loop. Then charge is going to flow on that loop, out of the battery, through the loop, and into the battery. So if I have charge moving in a circle, that generates a magnetic field in the perpendicular direction. You have a magnetic field run through here. Or you can change a magnetic field, and that causes charges to flow. The two are always together. So a good real world example is our world. If you go down to the core, not the very inner core because it's solid, but right above that you have a liquid layer, as we'll learn later in the course, a liquid iron. So it's a metal, and charges move very easily through a metal. And since Earth is spinning, it churns up little eddy currents. And so you have charges doing just what I drew here, not with the battery, but charges are being forced to move in these little circles, and so that generates magnetic fields around that little eddy.
I have a question.
Yeah, go ahead.
I understand, like, with the particle moving up and down, how it creates a wave, but how does it create a wave going in a circle?
So, yeah, that's a good question. Any way that you shake charge will make a wave. The up and down is perhaps the simplest way of shaking charge, but here you can imagine. Well, let's see. The light would probably, the waves would go in the same direction as the magnetic field. So if you have an observer over here or another charge over here, positive or negative, then as it's moving from one side to the other, if it was just straight back and forth, you'd have a traditional wave. But if it's going in a circle, it's going to be kind of a cyclical waves, like that. And then when this charge feels it, it's going to want to move in a circle to respond as well.
Okay, that makes more sense. Thank you.
But even light emission aside, it will also generate that magnetic field. In case of the Earth, all these magnetic fields add together to give us our global force field, which prevents a lot of high energy particles from getting through and raising cancer levels. It keeps us safe. And you don't think about it, but it is much more powerful than the gravitational force. I mean, I could demonstrate that pretty easily. Got a couple magnets here. I just got to keep them away from my computer. I'll put it over here, one magnet. And just to show I have another magnet, and you know what will happen, but if you think about, oh, sorry, .cam. If you think about it, we have the entire mass of Earth holding this down. So gravitational field associated with the mass of the entire planet, I can easily overcome it with another bar magnet and overcome gravity's desire to hold things put. So it's a very powerful force. Gravity is by far the weakest of the four forces. It just, we normally are thinking about such large accumulations of mass that it can be countered out. But even with a moderately strong magnet, you can still overcome the gravitational field of the planet. Okay, so if light is just a ripple in the electromagnetic field, oh, I think I have one more figure before I get to that. Yeah, just a final figure here. This is what a physicist thinks of when you say light. In fact, if you want to mess with a physicist, just go up to them and say light and then run away. And this image automatically pops into their head. You think of light differently, but this is how we think of it, as a ripple in the electromagnetic field. You have an electric component, and perpendicular to it, you have a magnetic component. Okay. So the next topic, but very much related, is making light. And we kind of touched on it here with the idea of moving the charge in a circle and how that produces a wave. Now, there are all sorts of ways you can shake charge. If you want to make light, all you have to do is shake charge. You can have a nice sinusoidal shaking, like I demonstrated with the cell phone tower example. You can have circular shaking, as we saw there. You can have random shaking, just charges bouncing around will cause ripples in the fields emanating from those charges. Not nice sinusoidal ripples, but herky-jerky ripples, but that's still information and energy getting out. All sorts of ways you can do it. You can have a magnetic field. If you have a strong magnetic field, charges will change their direction and start to oscillate around it, and hence emit light. We call that synchrotron light, synchrotron radiation, something we'll talk about more in Astro 102. In 101 here, the example I'm going to give you is anything with temperature. And we call this black body radiation. Or sometimes it's just called thermal radiation. And it's all about temperature. So what is temperature? Temperature is just a measure of the average particle speed. You have a collection of particles. What is the average particle speed? Or to put it another way, what is the average particle energy? Something that's moving faster has more energy, moving slower, it has less energy. Temperature is just measuring the average for a collection of particles. For example, the air in the room, my room or wherever you are, you feel either warm or cold, and that's because the particles have a range of motions. Some are moving fast, some are moving slow, but there is an average for that room, and that's what's determining the temperature. If you inject more energy into that gas, by heating the air, then all the particles are moving faster, the average is faster, and so it's a higher temperature. And it's true not just for gases. Well, for this figure here is, I'll get to liquids and solids in a second, but again, the air in your room, you'll have a distribution of speeds, and it actually looks something like this, where this is the average speed, and then you have many particles that are moving slower, and also a tail of particles moving faster, and I can inject more energy, but this is still going to be the distribution, as I'll demonstrate in a second. And it's not just for gases, but also liquids and solids. With liquids, the particles are bouncing into each other, and with some average speed. If it's a higher average speed, it's a hotter liquid. And even with solids, where they're connected to each other, that's what makes a solid. The particles are connected to each other. Like here, we have a complicated molecule. They're bouncing around. As I inject more energy, as I heat this molecule, it shakes faster and faster. As I take energy away, it shakes slower and slower. If I take all the energy out of a system, liquid, solid, or gas, what is the corresponding temperature? What do we call that?
Absolute zero.
Absolute zero. Absolute zero corresponds to removing all energy from the system, all motion from the system. So it's absolutely still. And so that's the lowest temperature you can have. Let's see, I have a demo here, or simulation. So again, this is these are gas particles because they're traveling through space for some time before they bump into something else. That's what makes it a gas. Liquid, they're not bound to each other, but they're kind of always in contact with each other. A solid, they're bound to each other. So this is an example of a gas, and the different colors correspond to different speeds, different energies. And if you track one and just watch it, if something hits it and speeds it up, it changes its color to yellow or white, or if it slows it down to blue or violet. And you have a distribution. You see that distribution right here. And it's a little noisy because it's a small number of particles, but that distribution won't change. Let me inject more energy in the system. So now they're moving much faster. This distribution, it shifted to the right, but you don't see it because it's plotting it relative to the average. Relative to the average, it's still the same shape. And it's noisy because the small number of particles. I can increase the number of particles and it becomes a better representation of the true underlying curve, which you see there in white. And again, that is this figure right here. So it's all with respect to the average. me see what's coming up next. Yeah, so we have this distribution of speeds, and you know, it's not the speed that sends a ripple, it's the change in speed. If a particle bounces into something, either the wall or another particle changes its direction, then you're going to have a kink or a wave in the electric field. You know, if the particle's nicely bouncing back and forth, you have a nice sinusoidal wave. It's not really what's going on here. It's more of a random process where it gets a kick this way, a kick that way, a kick that way. It's like having a whip and sending down one pulse and then sending a pulse in another direction and a pulse in another direction, but you're still sending out energy and information. So you're sending out waves, just messy waves. And the high-speed particles, they're going to be running into stuff more frequently, changing their direction more frequently. And so they produce high-frequency waves, or in other words, high-frequency light. And then you have the slow particles over here. They usually will have slow changes in direction, and so they're producing the low-frequency light. So you can go from this distribution of speeds, since they're interacting and bouncing off each other, to a distribution of frequencies of light. So particle speeds, shaking, and then the light that you get out of that system. So this is a thermal spectrum, a black body spectrum, and it's, again, anything with temperature will produce this spectrum, and where we have frequency increasing on the x-axis, or you can think of it as wavelength decreasing. Those two are coupled, as we talked about. And then you have intensity on this axis. Let's put some more detail here. First thing you see, this is a powers of 10 plot. So every increment here is 10 times the frequency. And over here, these increments are 1,000 times the intensity, but you can imagine doing little subticks. So here, 10 times as much, 100 times as much, 1,000 times, so forth, so on, 1,000,000 times. So if you go up on this plot just a little bit, it really is a lot more light than the figure indicates, because it's a powers of 10 plot. And you see the visible part of the spectrum here. Visible light runs from, and I'll write this down on the dot cam. So the visible part of the spectrum is 400 to 700 nanometers. Those are the wavelengths. It's a very narrow part of the electromagnetic spectrum, from 400 to 700 right here, corresponding to maybe about 3 times 10 to the 14 up to close to 10 to the 15 hertz. Over here, you then have the ultraviolet and X-rays and gamma rays, and on this side, you have the infrared and microwaves and radio. And then we see curves here for objects of different temperatures. Again, the black body curve depends just on the temperature. So let's think about these different curves here. This one is 300 Kelvin, and that's kind of like room temperature. Maybe if the room is a little bit warm, but it's typical of the temperature of the room, of you, of the furniture, the walls, the air. It's about 300 Kelvin. And so you yourself are producing light, because your particles are bouncing around, shaking at just the right frequencies to produce this distribution. And it peaks in the infrared. And you see it has a long tail going down towards the radio, but a kind of an exponential cutoff as you go to higher frequencies. And it cuts off before you get into the visible range. And that means you're not emitting any visible light. We see you because of reflected light. But if we were to turn off all the lights, we wouldn't be able to see you. You can try this yourself. You can find a dark closet, lock yourself in, and see if you can see yourself. So a homework assignment for you. But you won't, because you're not warm enough, you're not hot enough to be producing visible light. But you are producing infrared. Infrared is also known as what? How do we sense it?
Thermal.
Yeah, thermal heat.
Thermal.
Yep.
So Dr. Riker, is this why, like when you heat up metal to a certain, threshold, it begins to glow because its particles have heated up enough to emit visible light?
That's right. And I'll demo that in just a minute with an incandescent light bulb. That's all that really is.
So if we heat up a human, they'll glow?
Yes, and so that's my next example. Imagine heating up a human to 1,000 degrees. I don't recommend it. I wouldn't volunteer, but they will glow. Yeah, anything will. And so here's 1,000 degrees. It's still peaked in the infrared. It's mostly heat. But now you see the exponential cutoff comes into the visible part of the spectrum. And you get a lot more red light than yellow and green and all the others. So it won't be much light. It's pretty faint, but it'll be extremely red. You heat something up to 4,000 degrees, and then the peak is pretty close to the visible, kind of right on the boundary. And so you have all the colors represented. Remember, this is a powers of 10 plot. So this is still 10 times as much red light as blue light. So something that's 4,000 degrees will be pretty red. Not this red, but pretty red and brighter. You go up to 7,000 degrees, the peak is now on the boundary between ultraviolet and violet. And so this will be kind of bluish. There's a little bit more blue light than the other colors. It's kind of a light blue. And if you go up even to higher temperatures, anything above 10,000, it's pretty much a straight line through here. The peak will be over here or over here. And even though the peak is in the ultraviolet, and we can't see ultraviolet light, we still see the object because it's also emitting visible light and more blue than red. But there's still going to be red and the other colors in there, and we call that thermal blue. Anything above 10,000, it's the same distribution, just more and more light, but the same distribution of that light, so it's a thermal blue.
So is that the reason for like the different colors of stars?
Yes, yep, absolutely. And I'll if I get far enough today, I'll ask you a question about that to ponder. Okay, so we see two effects here. We see the peak shifting as we heat up a material, and we see the overall level of intensity increasing. And those have names. Maybe I'll go to a fresh sheet here. So the first effect is the peak shifts. That makes sense. As you heat it up, the particles are moving faster, so in general, you'd expect higher frequency light. So the peak is shifting to higher frequencies. And that's described by Wien's law, with a W, but you pronounce it with a V. And it's written in most textbooks like this. It gives you the peak wavelength is 0.29 centimeters divided by the temperature measured in Kelvin. Now, this is not very useful. I have a more useful form of it. 2,900 nanometers divided by the temperature measured in thousands of Kelvin. And that's more useful because, as you saw, like visible light, I'll write it down here again, visible light is 400 to 700 nanometers, so this will automatically be in nanometers. Sometimes we write stuff in microns, where 1,000 nanometers is 1 micrometer. It's kind of the boundary between infrared and visible. So 1 micrometer is also called a micron. There we go. So let's just quickly work a couple examples, because I want to save time to demonstrate this. First, let's consider a 1,000 Kelvin object. So if the temperature is 1,000 Kelvin, then the peak wavelength would be 2,900 nanometers divided by 1,000 Kelvin over 1,000 Kelvin. And so that's 2,900 nanometers, which if we convert to microns, 2.9 micrometers. And either way you look at this, this wavelength is longer than 700 nanometers. So where would this be? In the infrared or the ultraviolet?
Ultraviolet.
Ultraviolet.
Yeah, it's a little confusing. Wavelength runs the opposite way. So long wavelengths are over here. Now, frequency runs that way. So it's actually in the infrared. If you're longer than 700, so 700 is, sorry, I'm pointing to the dot cam. 700 is red light, 400 is violet light. So if you're longer than 700, you're in the infrared. This is something that would peak in the infrared, though, and we saw that here with 1,000, it's peaking right here, but you will still have some red light. Another example, Let's do 10,000. In this case, 2,900 nanometers, and you're going to work some examples at the beginning of the next class. 10,000 Kelvin over 1,000 Kelvin, so that's 2,900 nanometers divided by 10, or 290 nanometers. That's shorter than 400 nanometers, so this is peaking in what part of the spectrum?
Ultraviolet.
Ultraviolet, yep. And that one's not on this plot, but you can imagine another curve that goes even farther, peaking somewhere over here in the ultraviolet. And even though the peak is in the ultraviolet and we can't see ultraviolet, we still see the object because it crosses the visible. And we would see it as blue, thermal blue. Let me show you some examples here. So here is a really cold cloud of gas, so cold that it's peaking down, it's only 60 Kelvin, so it's peaking down in the radio or the far infrared, and so it's depicted here with these contours, detected with the radio telescope, and the background is visible light, but here we have this cold object, and emitting primarily in the radio. Here's something that's a little bit warmer, 600 Kelvin. You can see the distribution here, peaking in the infrared, but there will still be some red color, and you can see the redness of the gas here. Here's our sun. Its temperature is 6,000, which puts the peak kind of between red and yellow, which would be orange, but then you tint it with a little bit of blue, and it makes it yellowish. And then here's something that's really hot, 60,000 Kelvin. Some objects at the center of this globular cluster. It's peaking out here in the ultraviolet, but it has a blue color to it. Let me mention Wien's law, and then I'll do a demo. I may go about 2 minutes over today.
Dr. Reckert,
Yeah, go ahead.
is the shape of the distribution completely empirical, or is there some like logical reasoning why there's more low energy emissions than high energy ones?
Yeah, it comes from, you can derive it from this distribution of speeds and how they're interacting, randomly bumping into each other. You can derive what the shape of this spectrum will be. And
So why is the distribution of speeds like that?
the distribution of speeds like that, that is just from, you have particles with an average energy, and so you can derive what fraction of them at any given time will have more speed and less speed. If we start them all with the exact same speed, they won't keep that because of their interactions. Some end up moving slower, some end up moving faster, and that can change over time. But you can work through the physics of it and you end up with this distribution of speeds, and then that will give you this distribution of light. It's a little bit beyond Astro 101, but you can derive it. You just have to trust me on that. Let's see. Instead of, well, yeah, let me just mention Wien's law. We'll go a couple minutes over today. It'll be worth it, hopefully. So Wien's law, sorry, not Wien's law. The second effect is Stefan's law.
Your dot cam.
Yeah, see.
Thank you. Is Stefan's law, and this is everything being more intense. As we increase the temperature, it gets more intense at every frequency, every wavelength. The peak is shifting, but it's getting brighter at all wavelengths. So we call this Stefan's law, and this one's pretty easy. The energy flux, which is the total energy emitted across all frequencies, emitted per unit time and per unit surface area of the object. So every square meter, every second is emitting a certain amount of energy across the entire spectrum. It is simply proportional to temperature to the fourth power. It's very sensitive to temperature. So if I double the temperature of an object, be it a star or an oven, how much more energy do I get out in the same amount of time per unit surface area? Twice the temperature, how much more energy flux? This is ratio astronomy. So
16.
16, 2 to the 4. So again, you're just able, we're now to the point where you can look at this equation and just see how it works. So the last thing I want to do is demonstrate this. I have a incandescent bulb, which is really just a piece of metal. It's a tungsten filament, and I can send electricity through this filament. And tungsten is a nice piece of metal in that it has very high resistance, a lot of friction. And so because of that friction, it warms up. So as I increase the voltage here, I'll start with just a little bit of voltage. We see not much light, that's Stefan's law, and it's very red. That's probably 1,000 degrees. That's why we put bulbs around these filaments, because they get really hot. As I increase this, I'm increasing the temperature of the filament, so it's getting brighter. That's Stefan's law. But at the same time, it's changing its color. It's getting a little bit less red, it's getting more yellow. And so now we're beyond yellow, we're into yellow-white. And if I go all the way to maximum, it won't let me go farther than that, but we're starting to pick up tints of blue. So that's Stefan's law and Beam's law together. As I crank it back down, you see the color change. The intensity and the color, they go together. And so the thing I want you to ponder, and there's a video for you to watch that I'm going to sign out of class. It's just 5 minutes. But someone mentioned before the colors of stars. The coldest stars are red. I can't see anything after staring at that light up close. Red. And then as you saw, the color shifted to orange and to yellow-white, then white, and you get blue-white. And I couldn't go beyond that because it has a limit. It doesn't want me to blow up the device. But then you get to blue, or actually that thermal blue. But what about green? Green is part of the spectrum here, the colors of the rainbow, but we have no green stars. So I want you to think about, why do we have no green stars? Why is this the distribution of stellar colors as I increase temperature? And then check out that 5-minute video. I've already put it on the YouTube site for the answer. Okay, that is it for today.
All right, thank you.
My pleasure.
Thank you, Dr. Recker.
Dr. Recker.
Dr. Riker.
Thank you.
Thank you.
Thank you. Thank you.
Could you go to the doc cam real quick again?
Sorry. I wrote that down as I was describing it. Red, orange, yellow, yellow-white, white, blue-white, thermal blue. Why no green?
So is this also why, in terms like, so with nuclear reactors when they're power on, it has that, the thermal blue light, is that be the explanation for that?
No, that is different. That's a Cherenkov radiation. So
Gotcha. Okay.
that is, I'm trying to remember, make sure I get this right. But if a particle is moving faster than it should through that medium, it will have to slow down and shed a lot of its energy. And it comes out as blue usually.
Okay, thank you.
Dr. Riker,
Yes.
could you go back to the page before with the formula?
Yeah. Yeah, I was kind of rushing through there at the end.
Thank you.
Okay, if there's nothing else, I'll reset for the next class. I accidentally set the room up with the waiting room. And although I've gone back and turned that off, it hasn't registered. So sorry if you're stuck in the waiting room for a while, but I have to accept each person individually, which kind of sucks.
I have a quick question.
Yeah, go ahead.
So for the exam that's coming up, how would you recommend we study for that?
Yeah, so the primary thing is the homeworks. I wrote those specifically to get you ready for the exams. The math questions in the homeworks are a little bit more challenging than what you'll see in the exam. So if you can do them, you'll be fine there. Also, they're the warm-up questions that I do in class, and I'll post those once we get done with lesson 3, a couple days before the exam. So you'll be able to study from them as well.
All right, thank you.
Yeah, but go back and look at the solution sets, the answer keys, and that should help a lot. All right, lots of people coming in now. Any other questions? Well, I just sit here and keep pressing this waiting room button. I said a minute ago, I accidentally set up a waiting room this time. So I have to admit every person individually, which is a little frustrating. Start in just half a minute. Let me see how many I can get in here before we get going.
The test is next Friday, right?
That is correct. Yep. Homework 3 is going to be due on Monday, and the test is next Friday. And I think we'll be back on schedule by then. It'll be multiple choice, 25 questions on lessons 1 through 3. Questions will have the same feel as the homework questions and many of the warm-up questions. I encourage you to Well, the way we would do it if we were in the classroom, it would be a 50-minute exam. And I would let everyone bring in one sheet of notes. I call it a cheat sheet, front and back, anything you want to put on it. Since we're in COVID, I'm letting you take the exam from home. I'm giving you 24 hours, and it's not timed. You can spend as much of that 24 hours working on it as you want. But I still recommend that you put together that cheat sheet. I think you'll learn a lot more from putting that sheet together, forcing yourself to go through your notes, consolidate all the information. We've learned a whole bunch of stuff with still more to go in lesson 3. Just the process of consolidating it and organizing it, you learn a lot from that, and that helps with the exam, I think. Also, the questions on the exam will be in order, just like the questions in the homework, and so that can be helpful as well if you're trying to figure out what equation to use to answer a particular question. It's probably going to be the order that you learn the equations and the order that the equations are in the ebook.
Is there somewhere that we can find all of the warm-up questions?
I will post them once I'm done with lesson 3 material.
Okay, thank you.
I have 1, 2, and 3 in a single PDF. And so once we get through lesson 3, probably the Monday before the exam, I'll post it that evening.
Thank you.
Sure. All right, I'll keep peeking over, and as more people find themselves in the waiting room, I'll let them in. But let's start with our warm-up question. This is from last time. So I'll read through it. I see most of you have already taken a stab at it here. So Young's double slit experiment, we have a single photon of light emitted by an atom. It encounters the double slit experiment, so a barrier with 2 slits, and then beyond that, a wall that is a detector. So we have 2 questions. The first question is, which is true? The photon travels as a particle passing through one slit or the other. Or 2, the photon travels as a wave passing through both slits simultaneously. And then the second question has to do with detection. So the photon is detected on the screen as a particle at a single location, or 2, the photon is detected on the screen as a wave with different intensities at different locations. So answer the first one, answer the second one, append those 2 numbers together into a 2-digit number, and then send that over to the interface here. Now I'll give you, another 10 or 20 seconds. All right, let's see how we're doing. You can keep submitting if you want, but we'll take a look at the numbers. Let's see, the lowest possible was 1, 1. The highest possible is 2, 2. Let's take a look at the numbers here. I think this looks good. Got the histogram, and it's a little close between 1, 2 and 2, 1. But since I'm a little short on time and a majority, at least between those 2, got it right, I won't send you into the break rooms. The answer is 2, 1. Let me admit one more person there. And let me just, again, go over this. This is kind of confusing. It doesn't make intuitive sense. And no one really has a great answer for it. It's just the way the universe happens to work. But here's Young's double slit experiment, same picture that was with the question. But if we send photons of light through one at a time, they slowly build up this pattern, which is the interference pattern. You only get that is, the only way you can get that is if the photon traveled through both slits, diffracted through both slits, and then those diffraction patterns interfered with themselves. So the photon is traveling as a wave, it goes through both slits simultaneously, interferes with itself. But then when it hits the barrier, it is a particle all of a sudden. When we're not looking, light and all particles, it turns out, travel as waves, but as soon as we attempt to detect it, to look, it's a particle. It's one of the great mysteries of science on the smallest scales. We don't have a great answer for it. It's just how the universe happens to work. Admit another person. Okay. So yeah, light travels as a wave, but it's always detected as a particle. And we spent some time talking about this last time. Any questions about that? I mean, if you find it disturbing, that is good because it is disturbing. Again, that's just how the universe appears to work. Okay, let's see. Next in the list, I promised to explain that polarization experiment I did at the very end. So maybe I'll just repeat it really quickly. Let's see, .cam, screen up here. I'll get you all out of the way. And I'll put up a blank page. Blank enough. Okay, so last time, as one of our tests for the nature of light, I guess I can turn this around. We talked about polarization. So there we have a polarizer. And here we have a polarizer that if I put it in the opposite direction, it blocks out all the light because light travels as a wave. If light was a particle, it would still make it through the holes between those two polarizers, but it's a wave, so it needs room to oscillate. And if I put two like that, it doesn't have the room, and so it doesn't get through. But then, just for fun at the end, I took another polarizer, I put it in at a 45-degree angle between the two polarizers, and then light gets through again. Not all of the light, a lot of it's blocked, but some light is clearly getting through. And I decided to give you some time to think about that. Does anyone want to venture a guess? As to how that light's making it through if I put yet another barrier in there between them?
Does it cancel out the effects of like one kind of sheet?
It doesn't cancel it out, but it does something to the light that makes it through.
Does it like return it to its original state?
Part of it, part of it. The other class couldn't guess it either, so don't worry about it. The other class focused on the idea of maybe one barrier bends it or changes it or diffracts it so its orientation changes before it goes to the next one. But it's actually a little different than that. It's components. So I can draw it out here. Again, I'm not going to test you on this, but it's kind of a nifty result, so it's fun to think about. So most light coming from space is unpolarized. You have all sorts of different polarizations represented. Some light's going this way, some light's going this way, some that way. And once you put up that first polarizer, only light oriented like this makes it through. And if I put up another polarizer perpendicular like this, then all that will be blocked as well. But instead, if we put up one oriented at a 45-degree angle, what it does is you can take this light wave and break it into two components, one oriented with the polarizer, one perpendicular. So the perpendicular component doesn't make it through, but this component does. It's not as much light. Some of the light does make it through. It's just the component of this that is 45 degrees. Then you can put that final polarizer, which is the perpendicular one, perpendicular to the original. And again, you can break this into two components. This component's blocked, but this component right here makes it through because it's then aligned with that third polarizer. So each time, only the component of the light that is oriented with the polarizer makes it through. If you just have two perpendicular components, nothing makes it. But if you put an intermediate one, it takes its component that can then get through the next one. Anyway, that's the explanation. If you're losing sleep over it, there you go. And any questions? And we'll move on to today's material. Okay. So let's see, we left off last time talking about the nature of light. Since we established that light at least travels as a wave, we still detect it as a particle, but it travels as a wave. That means light has all the various properties that waves do. They have wavelengths, they have frequencies, they have energies, and we wrote down the basic equations relating those things. And in particular, one equation, just to review slightly, was that wavelength times frequency is equal to the speed of light. It's equal to the speed of the wave, but the unique thing about light waves is they all travel at the same speed, which means you can convert. If you know the wavelength, since that's a constant, you can figure out the frequency. If you know the frequency, since that's a constant, you can figure out the wavelength. So with light, you can describe it in terms of frequency, and here we have frequencies increasing to the right, and you can describe it in terms of wavelength. Here we have wavelengths increasing to the left. You can use either or, since the wave speed is the same for all light waves. And so we talked about these different regimes, how they have different names, but really the only thing that's changing is the frequency or the wavelength, whichever way you want to look at it. And by specifying that, you uniquely characterize the wave. Let's see. So new material. Light is, traveling as a wave, but then the key question is waves in what? In fact, let's get a fresh sheet of paper and write that down. So waves, as think back to when we were first talking about waves, the thing that makes a wave is it travels through a medium. A particle is its own medium. It carries itself as it travels from point A to point B. A wave has to go through something. That something can oscillate or vibrate, but it stays put, and it's the energy and the information that makes it through the medium. So what is the medium? If light is a wave, what is the medium through which light travels? And there's the correct answer, which is subtle, and you'll probably only get it if you did the reading. And then there's the answer that almost everyone gives, which is incorrect. I'm actually hoping someone gives that first.
Air.
Air. Well, does light make it through outer space?
Nope.
No, it does. We see stars and things, so it's not. It does travel through air when it's here, but it also travels through the absence of air. So what would the medium be? What could it be?
The electromagnetic spectrum?
Yep, so the correct answer is the electromagnetic spectrum, and that's subtle and will require some explanation. What's the answer that most people give that's incorrect? In fact, I think the book even states this at one point incorrectly. They think the medium is the vacuum. So a lot of people think that, okay, since light travels through outer space and outer space is a vacuum, the vacuum is the medium. But that is not correct, and I just want to emphasize this because the definition of vacuum is the absence of a medium. Vacuum means there's no medium, and so you can't have a wave propagate with no medium, so light waves, they're not propagating through the vacuum. They travel through space, but there's a medium permeating space that they're actually traveling through and not through the emptiness of nothing. And that, as someone said, is the electromagnetic field. So the electromagnetic field is the medium, and the electromagnetic field is what generates the electromagnetic force. So let's just pause for a second and talk about forces of nature. There are four primary forces of nature. The first one, or the one that everyone's most familiar with, is gravity. And this force of nature is attractive, always attractive, and it's between masses. And we've spent a lot of time talking about gravity. If you take Astro 102, we'll talk about it more in the context of Einstein's theories. And then you have the electromagnetic force. We used to think they were separate forces, electricity and magnetism, but they're actually two sides of the same coin. They're a unified force. And the electromagnetic force can be attractive or repulsive. And it's between what we call charges. Put up a figure here, show this. So we call these charges positive and negative, but they're really just opposites. The terms positive and negative, and even the term charge is something that we just applied as a stand-in. They have a property, they have two properties that are opposite to each other. If you have two particles with the same property, the same charge, they repel one another. They have opposites, opposite charges, they attract. So opposites attract. You've heard that phrase in other contexts, of course, and it originates here with physics, with the electromagnetic force. Let's put the doc cam back up for a second. So charges, which can be positive or negative, but again, we could have called it anything we wanted to. We could have called it up and down, black and white, you know, any opposites. And then there are two other forces. Does anyone know what the other two forces are? Forces of nature?
The weak and strong nuclear force.
Yep, the two nuclear forces. We have the strong and the weak nuclear forces. And the strong nuclear force is what holds nuclei together. If you think about nuclei, it's a bunch of protons and neutrons. Neutrons don't have any charge, but protons have a bunch of positive charges. And as we just saw, similar charges want to repel. So you have a whole bunch of protons in close proximity. Those nuclei just want to fly apart because of the electromagnetic force, which means there has to be an even stronger force that holds it together against that, and that's the strong nuclear force. And then you have the weak nuclear force, and that's kind of a weird force. It's a little non-traditional. It's responsible for nuclear decay, for changing one particle into another, and there's certain rules by which it operates. Those are more Astro 102 topics. Okay, let's come back to the electromagnetic force here. And as I said, you can view it separately. It has an electric component and it has a magnetic component. Let's focus in on the electric component first. And so this is a field diagram. It's showing the electric field. You can draw these things for the gravitational field as well. Here we have a charge. In this case, it's a positive charge. And we're drawing lines emanating from it. And close to the charge, those lines are concentrated. There's a higher density of lines. That just means the field is stronger. And so it will generate a stronger electric force. And far away from the lines are lower density, or far away from the charge, the lines are lower density, they're spaced out. So you can view that as a weaker field, and hence it generates a weaker force. It's just a way of depicting the strength of the field. Now let's say far away here we have an electron, which is oppositely charged, so it's going to be attracted to this positive charge, maybe it's a proton, and it will start moving towards it, slowly at first because the field lines are low density, that means a weak field, but as it gets closer, the field lines are denser, and so it's a stronger field, a stronger force, and it'll go faster and faster and faster as it approaches the positive charge. Okay, so that's a basic way it works. Now, what happens if we do two things? First, let's confine the electron so it can't move towards the proton. It can move up and down, but not towards the proton. And then let's shake the proton or shake the positive charge. So I'm just going to turn the doc cam around and demonstrate this. There's my table. Flip, flip. Okay, so what we have here is a metal pole. And the nice thing about metal is conductive, which means electrons can flow through it. Like the wires and the walls and everything, that's how we get the electricity to move. It's just electrons moving through metal. It's conductive, so negative charges, electrons can flow. Now let's say the styrofoam ball is a big positive charge. Now as long as it's not too strong of a positive charge, it won't pull the electrons out of the metal. The metal's conductive, so the electrons can flow through it pretty easily, but you have to have a really powerful electric force here to pull them off of the metal. Let's suppose we don't have that. So if I take the positive charge and I move it all the way up here, the electrons in that pole, where are they going to move? To the top, yeah. Some of you are probably indicating, but I can't see from here. And if I move it down, then the free electrons in this middle pole will move back down to the bottom. So if I go up and down, the electrons over here will do the same. But it won't be instantaneous. The force doesn't travel instantaneously. It travels at the speed of light. So there will be a delay. I move this up and then the electrons go up. I move this down and the electrons go down. But instead of thinking of it in terms of the charge, think of it in terms of the field, which will be the medium through which light travels. If we have a field line coming out here, right now it's high and then it's low and then it's high and then it's low. So the field line is looking like this as it's approaching the metal pole. So a wave. As I move the charge up and down, I'm sending a wave through the electric field that's emanating from that charge. So you can see that here. If I vibrate, if I shake a charge, I'm creating a wave in its own electric field, and then that will, you see it's getting weaker and weaker the farther out you go, but if there's a distant charge out here, it will then feel that wave and respond to it. And this is light. Again, light is a wave. It has to travel through a medium. The medium is the electromagnetic field. So if you want to make light, all you have to do is shake charge. Physically, that's what it comes down to. And we'll look at some examples of that. Let me bring up my slides here and see what's next. Yep, got it. So here's a common everyday example. I know this is a weird a weird concept, but here's, you make use of it every day. So your cell phones or your car radio, it works the same way. You have a metal rod, just like the metal rod I was showing on my table over there. In your cell phones, you have a little metal bar. We used to pull it out, the antenna, but now they're just built inside so you don't see them anymore. On your cars, you can see the antenna. And then you have a cell tower. And all that tower is doing is oscillating charge, sending ripples through the electric field that's already emanating from that charge. And those ripples are then felt by electrons in the metal bar in your phone. And you can encode, as we talked about, information in these waves. You can modulate the amplitude. So at the cell tower, I could do big oscillations of the charge and then small oscillations and then big oscillations. And I can code information into the pattern of modulating the amplitude modulation, AM radio. And then as those waves propagate out to your phone, the charges in that little rod will respond in the same way. That's an alternating current, and the electronics in your phone can interpret it and extract the information that was encoded and resynthesize the voice. Or frequency modulation, which is, I think, what these towers use. I can't remember, but I think that's the case. So they're taking this charge and they're shaking it at a high frequency and then a low frequency, and a high frequency and a low frequency. Again, sending information through is just reproduced by electrons in the little bar, in the little antenna in your phone. And it can work the opposite way as well. You can shake those and send a signal out that can be picked up. So that's how that information is being sent back and forth. It's because we know light is a wave and we can encode information into it. So that's the electric component. We said there are two components, the electric and the magnetic, and these two always go together. Now we realized this over a century ago, 1 to 2 centuries ago. For example, consider a battery here. It has a negative terminal and a positive terminal, and you can hook up a wire, making a loop. This is a simple circuit, and the electrons, the electricity will flow through that circuit. And so it's flowing like this. And if you have an electric field, if you have electrons moving in a loop, then that will generate a magnetic field. Magnetic field will be perpendicular. You can change a magnetic field to make an electric field. You can change an electric field to make a magnetic field. These two always go together. And a good example of this is Earth itself. Down in the core, as we'll learn once we get back to solar system objects, not the absolute inner core, but the outer core is liquid. It's liquid iron, which is a metal, and it's conductive, so charges can flow. And since Earth is spinning rapidly, that sets up these little eddy currents down in the outer core. Basically loops, just like this. Charges going in loops, and it generates magnetic fields. And those magnetic fields add together to give us our global defense system. Our magnetic field protects us from high energy particles coming in from space and keeps the cancer rates low because of that. So the two always go together, and we'll talk about the generation, how you actually make light in a second, taking advantage of this idea of shaking charge. But I'll just end with this diagram here. This is what a physicist thinks of when you say light. This diagram, a wave in the electromagnetic field. The electric and magnetic components are orthogonal to each other, but it's a wave. In fact, if you want to mess with a physicist, you just run up to them and say light and run away. And this image automatically pops in their head. They can't control it. That's what they think of. I know you've always viewed light very differently, but this is what's going on physically. Okay, so explain this in a second, but how do we make light? Well, from shaking charge. There are all sorts of ways you can shake charge, and different ways give you different distributions of light. In Astro 102, we'll talk about using magnetic fields. If we have a strong magnetic field and electrons get caught in that magnetic field, they'll cycle around, and that's shaking charge, so it's going to send ripples through the electric field, the electromagnetic field emanating from that charge, and you get a certain distribution of light. That's called synchrotron radiation, a synchrotron distribution. In 101, we'll consider a different distribution, one that's a little bit more common, and that is a black body distribution of light. Oh, there's one thing I wanted to show you before I go there. I forgot to do it. I'll just do it real quick. Back on the magnetic field here. And I just want to point out that the electromagnetic force is way stronger than the gravitational force. We don't think about this, but that's the case. And I'll just demonstrate it really easily here. I can pull these magnets apart. There we go. I'll just put one on the dot cam. Okay. And it's being held down by the gravitational field of the entire planet. The mass of all of Earth is holding it down. And yet I can overcome it with just a little piece of metal here. And pulls it up there. And you've played with magnets before. You know how they work. But if you think about it, that's kind of impressive. Just this one piece of metal overcame the gravitational attraction of all the mass of Earth. And that just goes to show that the electromagnetic force is way stronger than the gravitational force. In fact, it is the strongest, or the gravitational force is the weakest of the four forces. Okay, so I was talking about making distributions of light. And I said we're gonna talk about how you make a black body distribution. Let me write that here. Black body radiation, sometimes called thermal radiation. And this has everything to do with temperature. So again, if we're going to make a distribution of light, we're shaking charge in a certain way. So consider, we'll start with like the gas in the room that you're in. Gas in my room here, the gas in the room where you are, the atmosphere. It has a certain temperature, and what's going on in this gas are the particles are moving around. They're bouncing off each other. They're changing the directions. They're changing their speeds. And these little particles have charges in them. So every time there's a bounce, a collision, a change in direction, a change in speed, you're sending a ripple through the electromagnetic field emanating from that charge. It's not a nice, smooth, sinusoidal variation, like you're shaking it up, down, up, down. They're kind of bouncing around in a random walk fashion, but every time there's a collision, it's sending a kind of a herky-jerky signal through its electric field, like sending one crack down a whip, and then the next collision and the next. But you're sending information out, you're sending energy out. And this is all a function of temperature. So temperature, what is temperature? It's just the average speed of the particles, average particle speed. So again, the example of the air in the room that you're at, there's a certain temperature you're feeling, and all that's reflecting is the average speed of the particles. Some are bouncing around faster, some are bouncing around slower, but there's an average. And if you were to turn the heat on and start to warm up start to warm up the air in your room, that corresponds to a higher temperature. That just means the particles are bouncing around more quickly. And this figure right here, this is the distribution of speeds that you get. And for any temperature, you have some average speed, and you'll have some particles moving more slowly, and you'll have some particles moving more quickly. The fast-moving ones can become slow-moving ones, the slow-moving ones can become fast-moving ones, but on average, this is the distribution of the gas particles in the air in your room. And it's not just for gas, it's for liquids and solids as well. With liquids, the particles are all really close to each other, in proximity to each other, bouncing off each other continuously. With air, there's separation between them, or gas, there's separation between them, so the collisions are a little bit less frequent. With solids, they're connected by intermolecular bonds, but they're still pushing up against each other. Here's a little demo of that. Here we have a complicated molecule, and it's shaking because it has some amount of energy. I should write that down. Average particle speed is kind of the same thing as the average particle energy. The more energy the particles have, the faster they move. The less energy, the slower. So if I were to take this molecule here and remove energy from the system, the particles would slow down. And if I extract, well, the particles would slow down, which means the temperature decreases. If I extract all the energy from that, such that all motion stops, what temperature do we call that?
Total zero?
Yep, total zero, absolute zero. And that's all that means, is the particles are not moving anymore. That you can't cool anything down below absolute zero because the particles have ceased to move. You can't have less motion than that. Let's go back to the idea of a gas. I have a demo here, or a simulation. So particles in a box, and the different colors correspond to different speeds, different energies. The yellow particles, the white particles, if you look at them, they're moving the fastest, and the blue and the violet ones are moving the slowest. And if you track them, you'll see they change colors, change their speed, change their energies as they bump into each other. And down here you see the distribution of speeds. And it's a little noisy because I have a small number of particles, but the white is an average, and that matches this distribution over here. And if I pump more energy into the system, speeding the particles up, you still have the same distribution. Remember, this is plotted around the average speed. All the speeds are higher now, but compared to the average, you have that same distribution, like you see over here. And to make it less noisy by increasing the number of particles, it fleshes it out a little bit more cleanly. Okay. So as these particles are bouncing off of each other, as I described, they're sending ripples out through the electric field. The high-speed ones, the particles that are moving quickly, are going to run into things much more frequently, and so you're going to have high-frequency oscillations in their electric fields, and that corresponds to high-frequency light being emitted. And the slow-moving ones generally run into things less frequently, and so you're going to have low-frequency oscillations in the electric field, so low-frequency light. So they're all sending these waves out as they bump into things. And so a certain distribution of speeds corresponds to a certain distribution of light frequencies. And this is the distribution of speeds that you get for a thermal object, gas, liquid, or solid. And you can go through the physics. We're not going to in this course, but if you do go through the physics, it corresponds to this distribution of light. I'm just checking the time here. I have about 14 minutes. Yep, we're looking good. So let's talk about this distribution here. We have frequency increasing down here. Wavelength goes in the opposite direction. Intensity here, and there's some peak. There's a long tail going down to low frequencies and an exponential cutoff at the high frequencies. And here's the same figure with a little bit more detail. First of all, this is a powers of 10 figure. If you look on the x-axis, every tick is a factor of 10 higher. And on the y-axis, every tick is a factor of 1,000, but you can imagine extra ticks there. So if we call this 1, this is 10 times as much light, 100 times, 1,000 times, 10,000, 100,000, a million. So if you go up on this plot just a little bit, it's a lot more light. So that's something to keep in mind. Now, another thing you see here is the visible range is really narrow. Most light is not visible to the human eye. Now, visible light is over a very small range. I'm going to write it down here. So visible light is 400 to 700 nanometers. So that's on the wavelength scale. Down here you can see 400 to 700. It's right around there. Where 400, that's the shorter wavelength. That's over here. So let me write that down. The shorter wavelength, that would be violet, the violet side or the blue side of the spectrum. The longer wavelength, that's the red side of the spectrum. Out beyond red, we have infrared and then microwaves and radio. Out beyond violet, we have ultraviolet, and then X-rays and gamma rays. So let's look at a few of these curves. These are curves of different temperatures. Here we have a 300 Kelvin curve. And 300 Kelvin, that's kind of like room temperature, a little bit warmer, but approximately room temperature, the temperature of you, the furniture in your room, the walls, the air. It's approximately 300 Kelvin. And so you get a distribution like this. It's peaking in the infrared. How do we sense infrared radiation? What do we call it? I think I asked this last time.
Heat.
Heat. Yep, heat. So something that's 300 Kelvin is emitting a lot of heat. Well, it's emitting most of its radiation in the form of heat, in the form of infrared. And then you have this rapid exponential cutoff that falls short of the visible. So something that's 300 Kelvin does not emit its own visible light. You do not emit visible light. I see you, but that's because light is bouncing off of you. That's reflected light. If you don't believe me, find a dark closet, close yourself in there and see if you can see yourself. Consider it a homework assignment, I guess. Now, if you do want to emit visible light, you have to heat yourself up. If you warm yourself up to 1,000 degrees Kelvin, which I don't recommend, it's not good for your health, but if you did, the peak would still be in the infrared, but you see the exponential wing here does cross into the visible. There's not much light, but the light you get is very red. You get some red, maybe a smidgen of yellow, and then hardly anything of the blues and the greens and the blues. So we warm it up, the peak is moving to the right to higher frequencies, and now we get a little bit of red light. So it'd be faint and red. If you heat it up to 4,000, the peak is right at the boundary between visible and infrared, and you still have a lot more red light than blue light. Remember, this is about a factor of 10, so 10 times more red light than blue light. So it will look red, just not as red as this one. Heat it up to 7,000, now the peak is at the boundary between violet and ultraviolet. You have more blue colors than red colors, maybe by a factor of 3. So it will look blue, just not pure blue. There'll be reds and things mixed into it. And if you go up even hotter, it's not shown on this diagram, but you go straight through at a particular angle and you peak somewhere out here in the ultraviolet. And any temperature hotter than that, although the peak is in the ultraviolet, and we can't see ultraviolet, it does cross the visible, and you have more blue than red, And that particular shade of blue we call thermal blue. So there are two things going on here as we increase the temperature. And I'll write these down and we'll work some mathematical examples, and then I'll do a quick demo to end the day. The first is the peak is changing as I increase the temperature. And the second is the overall intensity. The amount of light increases at all frequencies, at all wavelengths, as I increase the temperature. Let's take the first one first. So there's an equation called Wien's law, spelled with the W but pronounced with the V, Wien's law. It tells you where it peaks. So the peak wavelength, it's usually written as 0.29 centimeters divided by the temperature measured in Kelvin. But this is not really useful. Again, we measure light in nanometers. Visible light is 400 to 700 nanometers. And sometimes we'll mention in microns, where 1,000 nanometers is 1 micrometer, which we call a micron for short. A micron is kind of the boundary between visible and infrared. It's a little bit into the infrared. And so we would like an answer probably in nanometers. So we can restate this as 2,900 nanometers divided by the temperature measured in thousands of Kelvin. Usually with things like stars, we measure them in thousands of Kelvin. So let's work two examples here. First example is, let's say the temperature is 1,000 Kelvin, in which case the peak wavelength would be 2,900 nanometers divided by 1,000 Kelvin over 1,000 Kelvin. And that's just 2,900 nanometers. 2,900 nanometers is longer than 700, so this is peaking where? In the infrared or the ultraviolet?
Infrared.
Infrared, that's right. 700 is the red side, 400 is the blue or violet side. So this is peaking in the infrared, and indeed, here's that 1,000 Kelvin black body peaking in the infrared. But although the peak's in the infrared, it will appear red because some of the distribution crosses the visible part of the spectrum. Let's work one more. Running out of space here. Let's do 10,000 Kelvin. In that case, the peak wavelength is 2,900 nanometers divided by 10,000 Kelvin over 1,000 Kelvin. So 2,900 nanometers over 10, that's 290 nanometers. Is that in the infrared, visible, or ultraviolet?
Ultraviolet.
That's the ultraviolet. So that's peaking in the ultraviolet. And although we can't see ultraviolet, we'll still see that object. Again, if the peak is in the ultraviolet, it means the spectrum has crossed through the visible, and so this will appear thermal blue. I just wrote thermal blue. Okay, let me show you some examples here. Here is something very cold, only 60 Kelvin, a cloud of gas out in space, cold cloud of gas. Its distribution is peaking here in the infrared or even in the radio. So we clearly won't get any visible light. We have to look with the radio telescope and we can see the contours here. It's also full of dust, which is blocking background starlight. That's why it appears dark in the visible. Here's 600 Kelvin, still peaking in the infrared, but crossing into the visible a little bit, and you can see how red that gas is. Here's 6,000 Kelvin. This is our sun. Our sun is actually 5,800 Kelvin. Peaks here between red and yellow, so you'd expect it to be orange. But once you throw in a little bit of green and blue, it gives it this yellowish tint. That's why the sun's yellow. And here's 60,000 Kelvin, which means you're going to peak way over here in the ultraviolet. But again, you're crossing through the visible, so the stars, these hot stars, will appear thermal blue. Okay, that's Wien's law. Let's work Stefan's law, and then I'm going to demo this. I might run 1 or 2 minutes over, but hopefully the demo's worth it. So the second feature here, let me go back, is Stefan's law. As we increase the temperature, we get more emission at every frequency, at every wavelength. So Stefan's law says that the energy flux, what that is, it's the energy emitted at all frequencies per unit time, per unit surface area, the emitting surface, is proportional to temperature to the 4th power. Sorry, I'm writing on the doc cam. There we go. Stefan's law, energy flux, which is energy emitted at all frequencies per unit time, per unit surface area, is proportional to temperature to the 4th power. So ratio astronomy here. If I double the temperature, how much more energy is coming off of that object per time per unit area?
Double?
Not double. I'm doubling the temperature. So, but we have temperature to the 4th power. So it would be 2 to the 4, which is what?
16.
16. Yep, again, with this ratio approach, you should be getting to the point where you can look at the equation. If I'm doubling the temperature, I stick a 2 in here, but then I still have to do the math. 2 to the 4 is 16. So if I double the temperature of a star, of an oven, if I double the temperature of an oven, I'm going to get 16 times more energy coming out of it. Any thermal emitter. Okay, I'm going to now demonstrate Wien's law and Stefan's law using an incandescent bulb on a variable power supply. And I'm even going to try to show you the spectrum. But first, let's just look at the overall color. So here I have a bulb. And a bulb, it's just a piece of metal in there. It's a tungsten, an incandescent bulb anyway. It's a tungsten filament. It's a piece of metal with high resistance. So as I run voltage through there, there's a lot of friction. It heats up the metal, and it will glow. So I'll just set that there. And as I turn this knob, I can heat it up. So it's on a low setting now. We're not getting a lot of light. That's Stefan's law. But the light that we're getting is very red. In fact, if I bring it down a little bit, it's very, very red. That's probably about 1,000 degrees. That's why they put a glass bulb around it, so you don't touch it and burn yourself. Now, as I increase the voltage, I'm increasing the temperature in the wire, so the color is changing. There we have orange. Now it's getting yellowish. So I'm changing the color. That's Wien's law. And I'm changing the overall intensity. It's getting brighter. That's Stefan's. Orange to yellow, and then yellow-white. There's white, and then blue-white. And if I could keep going, it'd get blue, but it cuts me off there because, I don't know, it'd probably explode or something. Now I'm going to try something just for fun here. I'm going to try to show you the spectrum. I'm going to turn this towards me so I can see. What I have here is a grating. And if I hold it just right, you can see the spectrum in there. You see, it's really low right now. But if you look carefully, you can see the reds and the oranges and the greens and the blue. So remember that. As I increase, maybe I'll decrease it a little bit more. I don't know if that'd be enough light for you to see the spectrum, but we'll see here. Yeah, so there I decreased it more. So this is about as much red as we're gonna get, but we still have those other colors. But as I increase it, make it brighter, we should see a higher proportion of blue. It's maybe a little hard to see, but there's definitely more blue there than the red. I'll go up even more. Maybe if it gets too bright, it just kind of washes out. Yeah, there's a lot of blue kind of right there compared to the red. normally I would pass these out in class and you would all do it yourself. So just the last thing I want to mention here, let's write down that sequence of colors. We had red. I can't see anything after staring at that bright light. Red, orange, and then it went to yellow, and then yellow-white, and then blue-white. If we could keep going, it would be blue, our thermal blue that we've been talking about. But there are no green stars. Now, stars have all these colors just because we're changing their temperature, just like the temperature of that bulb. When that bulb was yellow, it was the same temperature as the surface of the sun. Again, that's why we put it in a glass bulb so we don't touch it. So we go through this sequence of colors, and starting like the rainbow, red, orange, yellow, eventually getting out to blue, but there's no green. And I showed you with the spectrum, I broke it down into the colors. You saw the green in there, but we don't see any green stars. So I want you to think about why that might be, and also watch that video. That's your homework. And so in the YouTube directory, I put a 5-minute video that answers that question. Think about it first, and then check out the answer. And then we'll move on from there next time. Okay, I'll stop, and if there are any questions, I'll hang around.
Thank you.
My pleasure.
Thank you.
Thank you.
Thank you. Thank you.
Thank you.
Would you actually be willing to show the graph that you have behind the dot cam right now? Thanks.
Going off of the peak wavelength in the graph, how can you, or like, at what point is it going to be like a white star versus a blue star?
Yeah, so a white star, and this kind of answers why there are no green stars. Now, when we were going through this sequence here, the dot cam, right where you'd expect green, we see white. So why is that? Why not green? Why white? Got any ideas?
Is it the combination of all the colors sort of washing each other out?
That's right. And so we're not going to spend much time on it next time. That's why I want you to watch the video. But if you look at a star that's just a little bit hotter than the sun, maybe about 6,500 degrees Kelvin, it peaks right here in the middle. And so you have similar amounts of red, green, blue. And so the human eye combines that to be white. If it's peaking in the green, since we also have similar amounts of red and blue, we see white instead of green. That's one of the 2 answers to the question of why we don't see green stars.
Okay. Also, will we be doing Hertzsprung-Russell diagrams in this class, or is that elsewhere?
That's 102. Yep.
Okay.
This class we end with the, we don't go much beyond the solar system. We'll go a little bit beyond, look at some exoplanets, but we start with stars in Astro 102.
Okay.
Or if you're going to be a major, it'd be 202.
Okay. Thank you.
Sorry, could you go back
Thank
to
you.
the other graph for a second?
Thank you.
Thank you. And while I'm copying this down, I want to ask, the first thing I thought about with the light emissions, is that why when a fire heats up and it gets hotter and hotter, like first it's like a dull red, and then as it gets hotter, it turns into like a blue and a white light? Is that the same thing, or is that something different?
I think that's different because those are chemical reactions. And as those chemical reactions are taking place, I mean, there's some component of it will be thermal, but it depends on what you're burning. You get different colors. In other words, they're emitting the heat part is emitting a thermal spectrum, but a lot of the reaction you're emitting at individual wavelengths, so line emission, which we'll learn about next.
Thank you. That makes sense.
Anything else? Okay.
That should be good for me. Thank you. Appreciate it.
Sure. See you next time.